Now we need to talk about the other type of depression, the large-scale low pressures. These are otherwise known as polar frontal depressions. They are created in a very different manner than the small-scale heat lows. The polar front depressions are found along the polar front itself. This is principally in the higher latitudes. At about 40 to 60 degrees, depending upon the season, they typically move from west to east across the globe. The process of their formation is complicated and a little involved. Essentially, there are two main processes that need to occur to create a mature polar front depression. The first is to do with upper air movement associated with fast currents of air called jet streams. If we look at an example in the animation, we can see that the flow converges in narrows. This narrowing causes the velocity of that airflow to increase. The effect of this is complicated, but it is sufficient to say that as a result of this, there are areas where we have net loss and net gain of air in the upper atmosphere. These can be split into zones, labeled A and C. In the areas labeled C, we have a net loss of air. In other words, air wants to leave this location horizontally. In this instance, air tends to leave the upper atmosphere more quickly than it is replaced by air from lower down in the atmosphere. It is this net loss of air in a particular column that causes a reduction in pressure at the surface. As a result, air will ascend from the surface to the upper level around area C. The second main process occurs near at the surface and needs to work in conjunction with the upper air process that we have just described. Within the temperate latitudes, we have warm tropical air meeting much cooler polar air. The boundary between these two different air masses is called the polar front. As with any boundary between two liquids, this will not be a continuous straight line. At some points along the front, we will find kinks, which are smaller regularities along the front. What is happening in these kinks is that the warm tropical air is intruding into the cooler polar air. As the image sequence shows, this causes the warmer to replace colder. This is an important point. If much lighter warmer air replaces the colder heavier air, then the surface pressure will drop because we have reduced the total weight of the column. This particular process occurs quite regularly along the polar front. However, if this occurs underneath one of the upper air sea zones, then the kink will develop further as warm air continues to replace colder. This will eventually lead into the formation of a large-scale polar front depression. If we now look at the fully developed depression from above, we identify two unique surface features. The line with blue triangles on it identifies the first feature. This is called a cold front. This is where we have cooler, heavier air advancing and undercutting the warmer, lighter air. The advancing cold front will cause some of the warm air to rise up and over the cold air, but also force it to move, much like a bulldozer. The movement of this warmer air creates the second important surface feature. The line with the red semicircles on it identifies the second feature. We call this a warm front. This is where we have lighter, warmer air over riding heavier, cooler air. The warm air between these two fronts is called the warm sector. Its characteristics control the weather within the depression. If you remember from Earlier, the low pressure was created from the intrusion of this warm air into the cold air, thereby reducing the surface pressure. Because this is essentially one of the main driving forces of the depression, some analysts have called these lows warm sector depressions, not polar front depressions. The movement of air and therefore the wind within these depressions is very different to the small-scale depressions. By knowing what the wind conditions are, we can better prepare for our flying. If the surface pressure is falling in the center of a depression, then it goes to follow that air must move in horizontally. This is similar to the small-scale depression. However, what is different is that the surface flow doesn't quite get to the center of the low directly. It appears to have a rotational flow around the center as well, exactly like that of the tropical revolving storm. The reason that there is rotational flow around the low pressure is due to the Earth spinning. The spinning or rotation of the Earth will cause air moving into the low to be either deflected to the right in the northern hemisphere or to the left in the southern hemisphere. This apparent force creating this deflection is known as the Coriolis force. It is sometimes referred to as the geostrophic force. In summary, we can say that air moves around these large-scale low pressures anticlockwise in the northern hemisphere and clockwise in the southern hemisphere. Now we have seen how the air flows around such large-scale systems. Let's now see what we might expect the weather to be like. The depression weather can be subdivided into the warm front and the cold front. Looking at the cross-section of a polar front depression, let's now take a look at the warm front since it will be this part of the depression that will arrive first. We stated earlier that at the warm front, we have warm, moist air being forced to rise over and above cooler, denser air. As this air rises up and along the front, the temperature will drop because of adiabatic cooling. This may call the air to the dew point and condensation will occur. As a result, clouds will form along the front. Because the slope of the warm front is so shallow, roughly 1 in 150, the clouds are developed have a broad horizontal appearance and are therefore more commonly stratiform cloud. This means layered type. These clouds can extend up to 600 nautical miles away from the surface position of the front. Looking along the front, note that at lower levels the cloud is much thicker and denser than those at higher levels. Therefore, if a warm front were to approach an area, we would see the cloud lowering and thickening. Firstly, we would notice the thin cirrus cloud at very high altitude, then the thicker cirrus stratus, followed by the lower outer stratus and finally, right before the front approaches the larger thicker nimbostratus. This is one of the most obvious ways of recognizing an approaching warm front. As a result of the slope of the front and the horizontal spread of the cloud, the precipitation would cover a very wide area in front of the front, maybe a few hundred miles. As the front got closer, we would encounter increasing amounts of precipitation. This may be lightened into mitten at first, but just in front of the warm front where the cloud is lowest and thickest, we may encounter much heavier, continuous precipitation. The type of precipitation is another important point. Because the air along the front is rising relatively gently, there is only moderate vertical uplift. It is therefore common to find a mixture of fine rain and drizzle, or perhaps snow if the temperature is low enough, falling ahead of the warm front. In special cases, freezing rain or rain ice may fall, but we shall look at this later. Other important issues for aviation are the icing and turbulence that may be encountered along the warm front. The icing will generally be light along the warm front because of the lack of vertical support. However, with orographic intensification, the vertical support is increased and the freezing level can drop. Under these circumstances, the icing can be very dangerous. It is essential then to analyze your location to point out potential intensification. Under special circumstances, the most severe form of icing can be found underneath the warm front. This is known as freezing rain or rain ice, but as we mentioned earlier, this will be discussed in detail within the icing lesson. Turbulence along the warm front can be explained in a similar manner to icing. Because of the lack of vertical motion, the horizontal passage of an aircraft through the warm front would not abruptly change. We would most probably expect moderate turbulence within the lower cloud